Ba-ba-da-ba-ba-ba-bum. It is I, Monaco, and I am here with your ninth and final lecture in the periodic table unit. We're going to continue our nuclear shielding talk, and we're going to start to explain the trends that we observe in the periodic table using the push-pull between electrons and nucleus to explain those patterns and what's happening and why. Okay? So we are on page 24 and 25, taking these notes in our big pack. So the first trend we want to cover is atomic radius of the elements. Here's a great picture. And it's easy to see from just looking at the data that the atoms get smaller as you go from left to right across a period. So as we're going across a period, atoms are getting smaller. It's there in the data, but the question is why? Why does this happen? Well, effective nuclear charge is increasing across a period, pulling the valence shell in closer to the nucleus. So if you want to do effective nuclear charge for potassium, let's just call it, I'm just going to pick a number, this isn't actually it, we'll say +1. Then calcium +2, +3. As you go all the way across, you're going to be up here like +18 or something like that, right? So the greater the positive charge in the nucleus is pulling on that one shell of electrons greater, the valence shell, and it's sucking them all in. So in this particular period, there's 4 shells, 4 shells of electrons, and as the nucleus gets greater and greater charge, it's going to grab that shell and pull it in closer, 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 all of them. It's going to pull all the shells closer in to the nucleus because it's got a greater positive charge. And as a result, since we measure the radius of an atom between the nucleus and the outside valence shell, that shell's getting sucked in, so the atoms are going to get smaller. Okay? Well, we probably have to explain the trend down the group as well. This is because, well, they get down as bigger and bigger as we go because we have more and more shells of electrons and more kernel electrons in between the nucleus and the valence shell. So they get bigger from top to bottom, boop, obvious to see there, because the valence shell is shielded from the nucleus's positive charge and creeps out further from the nucleus. So if we still have our nucleus, and down here, if we use cesium as our example, we've got 1, 2, 3, 4, 5, 6 shells. 6, 3, 4, 5, and even one more, 6 shells of electrons. And if cesium has a +1 effective charge, it's not going to be very strong at pulling on that exterior valence shell of electrons. So this would be a very weak interaction. And therefore, the atom's electrons spread out and they creep out further and further and further from the nucleus as you go down a group. Because remember, the effective nuclear charge decreases down a group because there's more shells of electrons that we're adding on. Okay, we'll do a lab on this stuff, graphing these trends. Hopefully that'll help us understand a bit better. Electronegativity value. Well, electronegativity is how hard an atom's nucleus pulls on electrons from another different element. Okay, so electronegativity values increase from left to right across a period. You can see here in our graphic. They're getting steadily bigger and bigger and bigger as you go to the right. And why is this? Well, effective nuclear charge, again, is increasing across a period, which pulls the electrons from the outer elements stronger and stronger. So, that being said, it can pull on somebody else's electrons stronger and stronger and stronger, which I think is our final explanation. Oh, no. Electronegativity decreases down from the top to the bottom because, from the top to the bottom there, because as you add more shells of electrons, you get more and more shielding effect. The kernel electrons in the middle shield the valence shell from the effective nuclear charge because effective nuclear charge is decreasing and the nucleus positive charge is unable to pull on those electrons from other elements quite so well. So the way I like to think about it is the greater positive charge in the nucleus, the tighter in the electrons get pulled in within the same shell, But as you add more shells, it gets weaker and weaker. So as atomic radius increases, electronegativity decreases, or vice versa. As electronegativity decreases, atomic radius increases. Ionization energy. This is how much energy it takes to steal one valence electron, the first valence electron, from an element. And of course, it's related to atomic effective charge and ionization energy and shielding, okay? Because we're talking about the interaction between the nucleus and the valence shell. Ionization energies increase from left to right. Why? Well, the effective nuclear charge is increasing from left to right. So those electrons are getting pulled on even more as the elements become more, have a higher effective nuclear charge on the right-hand side. And therefore, it's harder and harder to remove that valence electron. So electronegativity and ionization energy trend kind of travel together. Okay, as electronegativity increases, ionization energy increases. And it's inverse for the atomic radius. The atoms get smaller as you go from left to right because effective nuclear charge goes up, and it's harder and harder and harder to remove those valence electrons. Let's talk about top to bottom. Ionization energy values decrease from top to bottom within the group. Why? Well, effective nuclear charge is decreasing as you go. There's more shells of electrons shielding the nucleus from the valence shell. So it's easier and easier to remove that valence electron as you go down a group from, like, say, fluorine to iodine and acetine and stuff. Again, it's related to the atomic radius. The smaller the atom is, it means the tighter it's holding onto its electrons, and it's harder to remove them, and it's easier for an element to steal somebody else's because it's holding on to its electrons very, very, very well. Ions. Metallic elements like to form positive ions because they have low ionization energy and electronegativity, because the effective nuclear charge is very small, because the metals are arranged on the left side of the periodic table where effective nuclear charges are small. They lose their valence electrons when they make ions. They lead to positively charged ions because, again, electrons are negatively charged. So the net charge of a metallic ion is always positive, and it will be smaller than the atom that formed it because that valence shell loses the electron. The valence shell is gone. Now we just have the kernel shells being represented. And in this picture, the sizes of atoms, all the metallic ions form positive ions, and they're smaller than the atom that formed it, versus nonmetallics. They have high ionization energy and electronegativity because these guys scavenge electrons really well. They have high effective nuclear charge. So they have a really strong hold on their valence shell, or any shell of electrons for that matter. And they even want to steal electrons from other elements too. So that's why they're prone to gaining valence electrons to form ions. They like to gain here. And when you gain an electron, you're picking up a negatively charged particle, which puts your positive and negative out of balance, and the net charge is going to be negative. And the ion that's formed when you pick up a new electron goes into the valence shell, which then spreads out a little bit to make room for it. And so the atom forms a larger ion than the atom. So the ions for negative ions are larger than the atoms that formed them. This leads us to our last Google assignment in the classroom, okay, and some practice pages associated with it. Portion of the homework, you got to do that there. This is going a little too quick. Oops. So we want to come to class prepared to go over the last pages in our practice pack. And the explanations for these trends are going to be very, very useful in your graphing lab, where you're going to pick up the data off table S and graph it all to see these trends physically, and then explain them using this effective nuclear charge and nuclear shielding concept. Thanks for watching. That does it all for your homework. Oops, forgot to change this number. That shouldn't be an 8. That's it, we're done. And that brings us to the end of the unit and end of the quarter. So thanks for watching. Let's do well on the rest of this unit's assignments and finish strong, people. Let's keep it rolling.